In this video, we're going to solve improper integrals. We're going to start with type 1 improper integrals, which is where you're integrating over an infinitely large region with respect to the independent variable axis. So one of the limits of integration is infinite, one or both. And then either later in this video or it might be in a separate video, we'll integrate type 2 improper integrals, which is where you're integrating with respect to an infinite discontinuity. Okay, let's get started. So just looking at this, the way you think about this conceptually is just like it looks. So it's a definite integral from x is equal to 3 and then all the way out to infinity. There's no upper limit. It's just you go infinitely down the x-axis. And you might be thinking, well, how could this ever have a finite value? You know, you're integrating over an infinite area. How could this not equal to every time equal to like infinity? Well, this is the same idea as when we talk about infinite sums. In chapter 11, you can have an infinite sum converge to an actual value in some circumstances, and so it's the same idea when you're integrating over an infinite area. Okay, now the way that we solve this is we interpret it this way. This is equal to, so this is equal to, we imagine that, so we're going to be taking the limit as, and we'll say t approaches infinity, and we do a definite integral like this, 3 to t, right? So the upper limit is t, but if we take the limit as t goes to infinity, and that's the integral. Okay, so we first need to solve this. So if we say that u is equal to x minus 2, then du is equal to dx. So we've got when x is equal to 3, u is equal to 1. When x is equal to t, u is equal to t minus 2. Well, actually what we could do, let's just solve let's just get the antiderivative. That might be a little bit easier. So, okay, we've got u to the minus 3/2 du. Okay, this is, so minus 3/2 plus 1 is minus 1/2. So u to the minus 1/2 over minus 1/2 equals, so minus 2 over root u. Okay, so there's the integral. And now if we want to evaluate this from 3 to t. So then minus 3 minus 2 is 1, so minus 2. So you got 2 minus, okay, and so what we have is the limit as t approaches infinity of 2 minus, okay, so as t goes to infinity, this goes to 0. 2 over infinity goes to 0, so this goes to 2. So that's this improper integral. Okay, so the way we write this is equal to the limit as t approaches, and this is going to be negative infinity in this case. The lower limit is t, the upper limit is 0. That's it. And so we solve this definite integral to get a function of t, and then we take the limit. So let's come to the side and do this. So if we said that u is equal to 3 minus 4x, then minus 1/4 du is equal to dx. Okay, so let's see if we update the limits. When x is equal to t, u is equal to 3 minus 4t. Let's go ahead and do this. Let's update the limits. When x is equal to 0, u is equal to 3. Okay, minus 1/4. And then we've got 1 over u du. Okay, so integrating from 3 minus 4t to 3. Okay, so we've got minus 1/4 natural log of 3. Well, we can do this. Minus 1/4, and then we've got natural log of 3 minus natural log of the absolute value of 3 minus 4t. Now we can update. Okay. We can see that for this integral, t is going to be negative. Okay. So if t is always negative no matter what, then that means that 3 minus 4t is always going to be positive, because this will always turn into a positive no matter what. So we can just say natural log of 3 minus 4t. Okay. Now we can combine this natural log like that. Okay, so what we've got is we can take out the minus 1/4, the limit as t approaches negative infinity of the natural log of as t goes to negative infinity, 3 minus 4t goes to infinity, 3 over infinity goes to 0. So the natural log of 0, you can think about as this function approaches 0, it's going to be from this goes to 3 over positive infinity. So this is approaching 0 from the right, which makes sense for the natural log. That means this is approaching negative infinity. Negative infinity times minus 1/4 is positive infinity. So this limit is equal to positive infinity. It's divergent. So yeah, they want us to specify. So this is divergent, and this is convergent. Okay, so this is equal to the limit as t approaches infinity of right, because we're always going to end up with in the t, after we take this integral, doesn't matter what this variable is, p, x, whatever, we're going to end up with a function of t. So if we come off to the side and do this integral, so this is going to be minus 1/5 e to the minus 5p evaluated from 2 to t, right? The derivative of e to the minus 5p is minus 5 times e to the minus 5p. So we've got minus 1/5 times e to the minus 5t minus 1/5, so plus 1/5 e to the minus 10. So okay, so this is the limit as t approaches infinity, take out the 1/5 of e to the minus 10 minus e. Okay, as t goes to infinity, this goes to 0. And so this limit approaches e to the minus 10. So 1/5 e to the minus 10. This converges to, and it's equal to 1/5 e to the minus 10. Okay. The limit as t approaches infinity of okay. So if we come off to the side and evaluate this integral, so we see we can make the substitution that u is 1 plus x cubed, therefore du is 3x squared dx. 1/3 du is equal to x squared dx. So, okay, when x is equal to 0, u is equal to 1. When x is equal to t, u is equal to 1 plus t cubed. And then we've got, take out the 1/3. So we've got square root of u. Okay, and so u to the minus 1/2 plus 1/2 is u to the 1/2. So u to the 1/2 over 1/2 is 2. All right, so we've got 2/3 square root of u evaluated from 1 to 1 plus t cubed. So 2/3, okay, 1 plus t cubed. There we go. So we could take out the 2/3 here and then take the limit as t approaches infinity of so this goes to infinity, infinity minus 1 goes to infinity, so this diverges to infinity. Okay, in this situation, we've got an improper integral going from negative infinity to infinity. So it's both limits are infinite. Now, the way you approach these types of problems is, so you integrate, you split this up into two separate integrals. You integrate from, you say that the definite integral from negative infinity to any finite number you want of the function, plus the integral from that same number, that same finite number, to infinity of the function. And then you evaluate those two improper integrals separately, then add the results. Now, before you start a problem like this, one thing I would say you should always do is check to see if you have an even or an odd function, right? Because we're going from minus infinity to infinity. Now, this is kind of confusing because infinity is not a number, but the way you can think about it this way, like, okay, if we had an odd function, if this was an odd function, okay, well, we know from the properties of odd functions, if we're going from minus a to a of an odd function, so f of minus x is equal to minus f of x, then this is going to be equal to 0. And then if we have the same situation and we have an even function, so that means that f of minus x is just equal to the original function, then we can turn this into take out a 2 and then go from 0 to a of f of x dx. You could apply the same properties with improper integrals like this, and that seems confusing because infinity is not a number, but you can just think about it like so as you're going to positive infinity, you're going to 100 trillion, 200 trillion, 300 trillion. You're doing that same thing on the opposite end. Now, if it wasn't an even or an odd function, let's say it wasn't an even or an odd function, well then yeah, even though you're kind of going off to plus or minus infinity, like at kind of the same, following the same x values, the function is different depending on if you're at the positive or negative side. So you can't look at it like it's symmetric. In general, yes, infinity is not a number, but if you're integrating a function going, from positive to negative infinity, you kind of think about it that way. Like you're going infinitely far in the positive direction and infinitely far in the negative direction. In that sense, it's like the infinities are the same. I don't know. That's kind of confusing. But yeah, if you have an odd function or an even function, even with infinite limits, you can simplify it this way. Okay, so if we take a look at this, it looks like this is an odd function. And I say that because, okay, what is f of minus x? Replace x with minus x. Yeah, this is minus f of x. This is an odd function, so this is going to be equal to 0. And again, I found this confusing at first because infinity is not a number, but think about it this way, okay? We're integrating, we know that we can think about these improper integrals in terms of areas under curves, right? Well, if we're integrating an odd function, right, then the areas under the curves are the same to the left and to the right. Just one's like, okay, let's look at it from the standpoint of an even function. This might be easier, but it's the same idea. If you have an even function, let's say it's convergent, so something like so we know it's symmetric. You would expect if you take the definite integral from minus a to a, it's just 2 times the integral from 0 to a, or from minus a to 0. You would expect then, if you're doing an integral from minus infinity to infinity, that that would be the 2 times the integral from 0 to infinity, or from negative infinity to 0 for a symmetric function. That makes clear, perfect sense. So when you think about it from the standpoint of an area like that, then I think this makes more sense. And then it's the same idea with an odd function. If you're integrating an odd function from minus a to a, the integral is 0. Same thing from minus infinity to infinity. Okay, so this is the limit as t approaches infinity. Okay, so we know that if let's get this integral. So we know that we solve this with the half angle identity. We change sine squared of alpha into 1/2 times 1 minus cosine of 2 alpha. So we've got alpha minus 1/2 sine of 2 alpha evaluated from 0 to t. Okay, so sine of 2 times 0, so sine of 0 is 0. So all we have is t minus 1/2 sine of 2t. 1/2 t minus 1/4 sine of 2t. Okay. Okay, so this is going to oscillate between, like as t goes to infinity, this is oscillating. between, like, it's going to be between 1/4 and minus 1/4, because this is one, this oscillates between 1 and minus 1, this oscillates, so 1/4 times 1. This goes to infinity, 1/2 t, so infinity minus something oscillating between minus 1/4 and 1/4 is equal to infinity, so this diverges to infinity. Okay, so we've got of okay, so let's see, we've got using partial fraction decomposition. So okay, when x is equal to 0, all right, when x is equal to minus 1, okay, so we've got the limit as t approaches infinity of, so the limit as t approaches infinity of natural log of the absolute value of x evaluated from 1 to t minus natural log of the absolute value of x plus 1 evaluated from 1 to t. Natural log of the absolute value of t minus natural log of 1 is 0 minus natural log of absolute value of t plus 1 minus natural log of 2. So what we've got is natural log of the absolute value of plus natural log of 2. So this is okay. As t approaches infinity, 2t over t plus 1 we know approaches 2, right? Multiply the numerator and denominator by 1 over t. So this approaches 2. Natural log of the absolute value of 2 is just natural log of 2. So this is equal to the natural log of 2. Okay. We got t. Okay, let's evaluate this. So we're going to say that integration by parts, u is equal to z, dv is equal to e to the 2z dz, v is equal to 1/2 e to the 2z, and then du is equal to dz. So u times v evaluated from t to 0 minus the integral from t to 0 of v du. Okay, so plugging in 0, this just goes to 0, then plugging in t. Okay, and then the integral of e to the 2z is 1/2 e to the 2z. Okay, so now we've got e to the 2z evaluated from t to 0. So e to the 0 is 1. Like that. So okay, so what we've got is okay, as t approaches negative infinity, this approaches 0, this approaches 0, so this approaches minus 1/4. This converges to minus 1/4. All right, so we've got the limit as t approaches infinity. Okay, and you know, actually, I wish I would have mentioned this at the beginning of the video, but even with integrals like this that go off to infinity or negative infinity, you could still potentially have a, you know, you can have both types of, you could be dealing with an infinite discontinuity as well. Like for all of the problems so far, I should have been checking if going from 1 to infinity, is there like are we dividing by 0 at, let's say, 3, for example? Or is there a discontinuity at like 3? So with any of these types of integrals, even if you're going off to infinity or negative infinity, you need to check that if there's some sort of either infinite or any discontinuity in the interval. Okay, but we can see here there's not. Only x is equal to 0 is the only issue. We're going from 1 to infinity. So if we evaluate this integral, okay, we can say that u is equal to natural log of x. du is 1 over x dx. When x is equal to 1, u is equal to 0. When x is equal to t, u is equal to the natural log of t. And then we've got just u du. So this ends up being 1/2 u squared evaluated from 0 to natural log of t. So 1/2. Okay, so we've got the limit as t approaches infinity. We could take out the 1/2. Okay, natural log of t as t goes to infinity, natural log of t goes to infinity. Infinity squares infinity. 1/2 times infinity is infinity. So this diverges to infinity. Okay, so we've got the limit as t approaches negative infinity of okay, and so is this function continuous from 0 to negative infinity? That's the, you know, we want to check that, and it is. There's no dividing by 0 or anything if you're at any number from 0 to negative infinity. Okay, so if we say that u is equal to z squared, then 1/2 du is equal to z dz. Okay, so when z is equal to t, u is equal to t squared. When z is equal to 0, u is equal to 0. And we've got z dz is 1/2 du. So then we're just left with u squared plus 4. Okay, and we know that this integral is going to be 1 over 2 arctangent of u over 2. You know, this is the arc 1 over the integral of 1 over u squared plus a squared du is 1 over a arctangent of u over a. So 1 over 2, we'll combine that with the 1/2. arctangent of u over 2. And we want to evaluate this from t squared to 0. So arctangent of 0 is 0. So we just have minus 1/4 Okay, so minus 1/4 the limit as t approaches negative infinity of arctangent t squared divided by 2. This is going to be the arctangent of infinity, and I believe that's a finite number. So okay, t pi over 2 times minus 1/4, so minus pi over 8. Okay, we'll continue with more problems in the next video.